Thank you, Mark. Thanks. And yeah, again, also thanks for the inspiring presentations from Alex and Simon this morning. As Mark mentioned, they have made my job much easier. I would like to bring a sort of practitioner's perspective to this. So sharing with you examples that we have been working on with our customers, that is industry, governments, academia, everyone. Everyone is welcome in the purely digital ecosystem approach. So what I would like to talk about today is connecting digital twins, both semantically and syntactically, for enabling interoperability. And then I would like to demonstrate how these then go on to add value. So my name is Amit Bhave. I'm the CEO and co-founder of CMCL. And just to check now that we move to the next slide. Just to check, can you all see the slide named outline?
Yes, we can. We've got that.
Brilliant. Thank you. Thank you. So that's the outline of my presentation. So I'll just quickly introduce CMCL first, then talk about the sort of the intrinsic problem with regards to silos. This is data, information, knowledge silos across domains and sectors. Then I would like to present the solution that we are working on, which is called the World of TAR. It's very much a overarching architecture, a digital ecosystem architecture. So I would like to present that. And then I would like to cover 3 use cases, as Mark introduced. I would mainly talk about CReDo, so that's the cross-sector climate resilience on a sort of a regional digital twin level, covering sort of the east of England area. But I would then, as there have been a lot of chats about sharing the learning, sharing the outcomes, which I think CReDo and DT Hub have done an excellent job in terms of not just the reports and sharing the code environment, but also the key learning, so that hopefully others don't commit the same mistakes that we did. So I would like to then build on to that development and how CReDo has really inspired us to take on other work and similar other projects where sort of the underlying digital architecture and framework ideas are the same, and they're out in the open domain. So it's really welcoming everyone to that ecosystem. So in that spirit, I would like to present then moving from a regional digital scale to a city level scale, looking at a port city, again in the UK, but it doesn't need to be with the underlying framework. It can well be Singapore or Mumbai or anywhere else. And then from that port city level, I would then go on into a building level, so very much Lego-like. So starting from a sort of a small brick to joining those bricks into a large, let's say, large fort or castle. So going from regional to city to a building level digital twin. And I would like to give an example of laboratory automation. Again, that doesn't mean this is a digital twin purely for lab case, but to share the ideas behind it, because then it can be, the whole point is to be extensible and to be applicable across sectors and across domain. And I would like to summarize at the end and acknowledge the huge contributions made by the CReDo team, as well as the Dome team and Cambridge and CARES. So let's start with who we are. We are CMCL. CMCL stands for Computational Modeling Cambridge Limited. We are an organically growing company spun out of Cambridge. Tomorrow is our actually 16th birthday for the company. Our offering is the World of TAR. I'll go into details of what does that actually mean, and sort of digital services more so powered by the World of TAR architecture. The mission is enabling cross-domain interoperability, and again, I'll give you examples of these. And this is done via our team, which comprises technical specialists, our daughter company, CMPG, based in Germany, and our distributors in sort of India, China, Korea, Turkey, etc. So just a very quick background, and that is to do with, we spun out and we started work in the energy sector, in the decarbonization sector, but mostly looking at sort of ourselves working in silos. And this was important because we developed the expertise thereby. So we worked in sort of powertrains on how to reduce emissions from trucks and non-road power generators. We looked at how to produce carbon nanoparticles. What do these models mean from a physics side, from a chemistry side? And then we, at the same time, we're also dealing into sort of machine learning statistical models applied to organic photovoltaics, or even on a much higher system level models, where we looked at carbon capture and storage as or biomass power as any carbon negative energy technologies. What we realized is we can have an impact, but we can't have an overarching impact in an organization or in a field, which is when that connected mindset started developing. And over the last about, I would say, in a span of 5 to 8 years, and in the research front over 10 years now, but on a commercial front, in that last 5-year time span, we have been working with that connected mindset, because all these individual silos are intrinsically connected. And that's the sort of the birth of the world of TAR. The team behind this, again, we are 17 people here, 4 in Germany, so it's a small team comprising various technical specialists. But we are also part of the wider ecosystem of research, of collaborators, and CReDo is one such example. But here internally, before we go into the use cases, I would like to acknowledge the huge contributions from, for example, Cambridge Cares, based in Singapore, and Marcus will be presenting, I think, on day 3 of this conference in the Australia stream. So yes, you're welcome for that talk. It's our sister company in Germany, CMPG, as well as Como Group. This is the group at University of Cambridge, Department of Chemical Engineering, which is where we spun out from. So let's dive into then the problem space. I've introduced the company. In terms of the sector, so we work on interoperability issues, both vertically and horizontally. What I mean by that is interoperability exists within an organization. So it could be across teams, it could be across, even in one team, across different people, across different software standards, different software tools, data standards, etc. So it's within the sector as well as across sector. We would like to solve the interoperability problems. And these problems exist across sectors. I've just listed here 4. In terms of poor sustainability, inadequate resilience and adaptability of an asset, let's say not just economic resilience, but also say climate resilience, as well as ineffective decision making. And these 4 problems then again stem from 4 root causes, one being data and information silos, the other being lack of cross-domain accountability, low interoperability, and finally, as decisions are required to be made in a dynamic way, also with varying characteristics across length and time scale, so that makes it challenging. The 2 problems on the right-hand side, I would just give a quick note, because it sort of resonates with what Simon mentioned earlier about how to account for sort of intrinsically problems are multi-domain. And this means if you look at a city, a building, a region, and develop a digital twin, it's not just about, of course, not just about the technology, but not just about having a digital twin to give you an aspect. It needs to account for a variety of things here. So what I mean by that is, say, materials, infrastructure, health, environment, economy, resilience, society, etc. And this is also not a static picture. This in itself, the ovals can be added. And that's the whole point of being distributed, being decentralized, but also being agile and dynamic. And I'll give you examples of this and how the learning improves from it. The second point I wanted to talk about is low interoperability. And this comes in, it's kind of intrinsic in the way we design things. So there's a physical realm, then there's a digital realm. In the digital realm, of course, having so many stakeholders, so many players in it, which is a fantastic thing. The issue is each and everyone has their own way of describing the data, of contextualizing their data, of contextualizing their models, their software tools, the rules, and and sort of vendor-centric platforms. All these create interoperability issues. So how can we solve this and have a sort of a vendor-agnostic view? This is the key question that we are trying to answer. So I would like to present the work thereby in terms of the solution, what we name as the world avatar. The world avatar is all-encompassing. What I mean by that is anything that can be conceptualized can theoretically be made part of the model. So it's a world model and it's an all-encompassing model. It's connected by design because as we have seen, say a building is connected to the utilities it uses, it's connected to the people, those people are connected to other people, etc. So the view of the mindset here is very much connected and developing a shared understanding. It's scalable by design, and I'll like to give some examples of it. It's also self-evolving because it's not just important to map out the knowledge, it's also important to keep it evolving based on the new information that we gain, just like the humans do, but we should at the same time utilize the power of the machines around us. It enables interoperability through the use of ontologies. I'll go into the details of what that means very soon. And the distributed, it follows a distributed decentralized architecture. So with the world avatar, we aim at connecting data, software, models, and tools, both semantically and syntactically. You can query then this data in even a federated environment. You can query this using industry standards such as Sparkle. You can then imagine, so you can build parallel digital worlds like the metaverses, basically, where you can still have the base world connected to these parallel worlds, and then you can really run holistic scenarios by changing things in those parallel worlds, while at the same time, any change in the real world around you is propagated in those parallel worlds. And sort of the classic management control optimization, you can always use that to optimize and control and improve the base world, that's the real world around you. So that's the four quadrants in which we are working. As we'll be using the terms physical twin, digital twin, connected digital twins, I just want to maybe use just a quick one to explain how we think about it. It's very much Lego-like and modular. So you can see here in sort of hierarchy, there is a component level, then to a process plant or an energy plant, to a whole city, to a full region with the entire natural and built environment, etc. So you can have the real world. You can learn from the real world through sensors, through data, and at the same time, you can build twins at these levels of hierarchy. And through the real world and the twins, you can have a constant input in terms of data and models. And on the right is the sort of the bare bone sandwich layer of the world avatar, where, again, this is a bit crude cartoon, but essentially what it comprises then is you need autonomous agents. These agents are responsible for taking in that data and processing the data, or running models and executing software, not just ours, but also third-party commercial software or confidential and open data, etc. And then also outputting the information that's in a useful format, whether it's through a chatbot, whether it's through a web portal like CReDo, or through a mobile app. But these agents are also part of are described through the ontology. And these agents are part of the underlying dynamic knowledge graph. What the knowledge graph does is it connects different concepts and instances via the relationships, and that's how we build and go on building the knowledge. Once we have that, then you can, as an output, you can then provide these insights and interventions, not just to the real world, but also in the digital world to update and improve the knowledge constantly. So it's a very much dynamic, sort of self-improving framework. So I mentioned knowledge graphs, and this is when I introduce concepts and instances. I'm sure, I mean, on day 2, I see a lot of talks with this topic, but just what we see here as a knowledge graph for those who are new to this or who may be new to this is there are different concepts, such as, for example, a property. Then there are different instances. So a building 1 is type of that property. So between the concepts themselves, there can be relationships. And between the instances also, there can be a relationship. For example, a building 1 has an owner, and owner has a name, in this case, say John Smith. The building 1 has an address, a specific address as well. So it's really important to capture the concepts, the instances, as well as the relationships between them. And that's what's the underlying knowledge graph here. So the output of the information or the access, as I mentioned, it can be done in a variety of things. In this case, it could be a mobile app on the left-hand side, or the CReDo visualization on the DT Hub. This is open and live with, of course, with synthetic data. But you can play with that as an output and access that information, or it could be a purely desktop agent, a desktop software, as well as chatbots such as Zaha, for example, and I'll go into details of that during the CReDo showcase. So I think let's dive into the use cases, but I wanted to take a different view and a different approach in this case. I would go with the unique value points here in terms of the work that's been done. And through each value point, I would then like to route it to the showcases. So just to introduce you, first of all, the value points. The first one, and this is, again, a huge thanks to the CReDo team and the wider stakeholder community involved with CReDo, is the data sharing and the distributed data architecture. Again, Simon had covered this in his talk, so I won't go into the details of it, but it's really where we have built, as we are working across 4 sectors, telecoms, particularly in CReDo, telecoms, water industry, power industry, and healthcare, so hospitals, dentistry, etc. So across these 4 industries, it's important that the data owners retain the control of their data, because this is confidential data. But at the same time, we have the ability to combine that confidential data with open data as well to make collective shared understanding and decisions. Again, during the showcase, I would like to demonstrate that. The second UVP is the World Avatar's derivation framework. What this means is, once you have an information that's updated somewhere in the real world, how does that information really traverse through the knowledge graph, it updates the knowledge itself, and how does it evolve the knowledge graph as a dynamic entity? And this again, I'll present a showcase or use case dedicated to this. And the third one, which will be on the lab automation, this is to show that, of course, there are plenty of vendors, there are plenty of data formats, there is heterogeneity. How do we tackle that problem? And again, as I said, lab automation is just one example, but the aim is to really show how we to share how we do it and to get your feedback on it. But the key thing is, how can we be then platform agnostic? So these are the 3 showcases I'll be covering. So starting with CReDo as a regional digital twin, then a port city for the maritime air quality, and finally lab automation. Many of these are sort of, we look at it very much Lego-like, as I said, in a modular hierarchical way. And the aim is always to, for example, to have a better world around us. So either to reduce the costs, then at the same time to reduce our energy carbon footprint, as well as, while doing that, sort of how to attain clear goals, such as in this case, UN Sustainable Development Goals. So the first example is CReDo. In CReDo, essentially what we are looking at is 3 different assets. And let's say the box here in blue, that gives you the flood level, and that brings down the power industry assets, in this case, the secondary power station. If this is the primary, this is, let's say, for the time being, the secondary power station. But this power industry also supplies power essentially to the telecoms industry, to the water industry, and to the healthcare. So if you just built in resilience thinking about one sector, in this case, power industry thinking about its own assets, or water industry thinking about their own assets in silos, then the resilience is just not strong enough. And as a nation, or as a region, we do suffer from that lack of resilience. So to solve that, we have developed the distributed architecture, as I said, in which case you can have the different data coming from different owners, in this case, the water, power, communications, as well as other asset owners. They can have access, and they will retain access to their own data, in this case, the power, telecoms. But at the same time, based on the data agreements in place, they can also share the understanding while not giving away the ownership to their data. And this is really crucial in a distributed architecture. So once you have that underlying framework, which was a tough deliverable, you can then look at how to establish this and how to build the knowledge graph. So this, for example, shows you a snapshot from DT Hub, Digital Twin Hub, where you can represent different types of floods. So in this case, fluvial, pluvial, as well as coastal flooding. And on that, you can map geospatially the different assets from these 4 different sectors, so healthcare, power, water, and telecoms. You can also see that some of the assets are covered in red rings and some of them with orange, and the others are absolutely safe and fine. So what happens with red here is it denotes that the asset is down due to primary failure due to flooding. But some of the assets which are down here shown by the orange circles, that's because it's a secondary failure. So they depended on the primary failure in terms of the operational and the business logic, and that's where they have failed. If you then zoom into an individual asset, you can get the metadata on these assets. So you can get the level of flooding, what would be the total economic cost if you were to build resilience for that, whether it's lifting the asset up in terms of elevation, or whether it's wrapping it in plastic, for example. But the steps and the costs behind it, that should be known. It also helps us, I think in the previous talks, they also talked about, I think Alex mentioned resilience of assets as the key thing. And this is an example where we looked at 2 NHS hospitals here on the lower side, one due to primary failure, and the second one has lost power on the top right side due to a secondary failure. So the knowledge graph helps you identify those nodes and those concepts here, instances here, in this case, the primary power station and the secondary power station, where if you build that resilience, then you can have at least the critical infrastructure, such as these operational in case of a flood event. I won't talk about dashboards because that's an obvious output agent. What you get here is an aggregated view across the assets, how critical the assets are, what are the failure rates, etc., and how to build resilience around it. But then the beauty of knowledge graph is that you can actually extend, you can have it extend and scale to other sectors. In this case, then we map out the entire road network, because then if an asset is down, you would like to see, how do I reach that asset? What is the best way of reaching it? Is it to rescue people, for example? Is it to rescue the critical infrastructure assets? Do I send an ambulance? Do I send a whole fire truck? Or do I need an amphibious vehicle? And depending on that, you combine the road network with sort of the routing algorithms. It can also help you with the isochrones. In this case, the isochrones stand for any travel times from a central point, so in this case, a hospital, and you can quickly identify vulnerable population that is unreachable. Again, using the same extension, the same knowledge graph developed in CReDo, but with an added sort of sector or added domain of transport here. You can also identify critical roads based on the knowledge graph frameworks, where you can then focus on the resilience. As we talked about sharing the learning, there's plenty of information on the Digital Twin website. What we are also doing is trying out some of the ways of reaching out to audience through NLP, through natural language programming. This is, for example, Zaha, a chatbot where you can ask questions in natural language, and it turns those queries into Sparkle, and at the same time, it gives you the response. So with Sparkle queries, which can be complicated at times, you can use those in different knowledge graphs, and at the same time, you also get information in natural language. I'm aware of the time, and hence I'm not going to demo it live, but I can send information on this out. I'll skip this bit, just move to the example where recently we saw that the cruise ships can cause a bit of air quality issues at ports. This is because when they are docked, then rather than, for economic reasons, rather than going into a electric mode, they continue to run with gas oils and other heavy fuels, which can cause airflow issues, which can cause air quality issues. So we tackle this interoperability problem by representing the whole sort of cross-domain. So right away from describing ships ontologically, describing weather and weather patterns, city architecture, as well as really the chemical species and the atmospheric chemistry that's going on. And this is a case of sort of combining software that's third-party, open source, confidential, data sources such as live ship locations, weather, live weather, etc., and really going and deploying a virtual sensor, in this case for the port of Southampton, where we saw that once you deploy it and if you detect, say, a cruise ship in this case, you can then track as an emission source point, what are the gas phase and particulates, and then how do they permeate through the atmosphere, say as a function of time, how is it looking in the morning, afternoon, evenings, as a function of wind direction, wind speed, etc., etc. And the final bit is going one level down in terms of focusing now on a building and a lab within a building. But again, there is a plethora of systems and platforms when you look at a lab. And this could be lab information management. This could be the building site, so BIM models as well as BMS, as well as the actual scientific experiment that's going on and the data that's being produced. So based on that, we covered 3 personas where we can apply this interplay and solve the interoperability. We can thus help a research facility manager through a query app. We can have a research lab manager working with the asset management app, or actually a research scientist performing the experiment both in person as well as virtually. So here we integrate lots of different data sets. One clear application of this is if you have multiple vendors. In this case, for the lab, we had 5 vendors with individual platforms, with individual data formats. And what we really needed was to enable interoperability across the vendor data, as well as to have access. So similar to CReDo, where not everyone has access to everything. It depends on the data sharing agreements, etc. And then you can have the output that adds value. So I've tried to demonstrate value of enabling cross-domain interoperability via 3 use cases. We've developed the distributed architecture as well as context-aware and autonomous agents, and I've tried to explain how they add value. And more than happy to take any questions, and please do engage with us as part of CMCL, as part of CReDo, etc., on helping develop and deploy digital ecosystems towards net zero and sustainable development. So thank you.
Amit, thank you very much indeed. And you've managed to cover an immense amount of ground as well. I suspect that lots of people will want to follow up, and I think that John Holden has put a link in the chat which will help people. So I would encourage people to do that. Amit, we are a bit short of time, so I think if you're okay to hang on for just a little bit longer, then we'll go to one question, and I'll ask Arthur to pose it.
Yes, certainly. Which one did you want me to deal with?
Whichever you choose to go with.
There you go. I mean, this was as you probably realize, a perfect foundation for the work that we've been doing with our digital twin, which we're going to be talking about in a few hours. But my big question to you is, in the distributed architecture, there are individual data contributors, and those contributors are going to be sensitive about the data that they're supplying. I'm curious whether you have something built into the world avatar that ensures the privacy of the data that is being contributed from those multiple players. And just for context, what we're trying to use is differential privacy, but we haven't successfully integrated it into the twin yet. Did we lose him?
I don't know. Let me just have a quick look to see if we did. Oh.
Yeah.
Oh, he's still there.
I think now I can unmute. Sorry, I was not, it said I didn't have the power to unmute.
Oh, we gave you the power, man.
Thank you. And Arthur, it's inspiring to see what you're doing, and really excited to looking forward to that and learning how you have taken this further. So thank you for your question, an absolutely cracker of a question. And I think I would like to answer it based on, this depends really on what TRLs the solution you wish for. Remember, in CReDo, we have solved this. This is very much a demonstrator as a connected digital twin. In case of the maritime air quality example, we have done this using blockchain technology, hyperledgers of this world. And we have also done this via engagement with other data spaces in Europe, where there are standards for authentication and access rights, etc. So I think the whole point is that, I mean, you have nailed the point that yes, there will be confidential data, which means access rights issues and authentication issues, and this needs to be dealt with. We have dealt with that in all the three examples that I showed. Whether it's on a commercial TRL 9 level, I can't say that, because we are dependent on the solutions themselves, the individuals. We can certainly incorporate those, such as Hyperledger blockchain, or in this case, a data space authentication and sort of authentication and access management. So I'm talking about the European data spaces here, and we have experience with those. But that's inherent to all three use cases.
Great, thanks.
Fantastic.
Thanks very much.